Welcome to SM219 Lecture 36. Today we'll be talking about inference for regression models. These slides have been derived from UC Berkeley's Data 8 course from the fall of 2018. We'll be talking in this first lecture about the regression model. The model, the assumptions about how the data were generated that we're looking at, say that the data is generated as a signal plus a noise term. The signal refers to the fact that we believe that we have x and y coordinates being generated in the following way. For a given x, the y is the slope of some kind of line times x plus the intercept of that line. And we think of that line as being the true line, a true regression line, that underlies the generation of these x and y pairs, but we don't actually get to see that true line and the results of the x and y pairs on that true line. Instead, we observe those y values plus some noise. And that noise we assume to be randomly determined, randomly drawn from a normal distribution that has mean zero and has constant variance or standard deviation across all the different x values. So, for instance, we might get this first point, which would have been generated if it lay exactly on the true line to be here, but in fact we observe the correct y coordinate plus a vertical noise term, which puts the point up here. And then for each different point, we pull it off the line by this noise term. And what we don't get to see is this true regression line. We actually only get to observe these points. And then we try to fit our model to predict what the true regression line would have been given these points. Seems kind of almost like magic. Let's see it in practice in the regression model. Here I'm looking at the Day36 class notes, the demonstration, and to start, let me just say something about inference before we get into the regression model. If you have a sample of observations relating to quantities in x and y coordinates, we can fit a regression line to the sample and predict the relationship, or even the value of the response variable given a value for the predictor variable. However, you might be concerned that our predictions depend on the sample that we start with, and they do. So you might ask, how much would these predictions change if we had a different sample? If you had a different sample, how would your regression line change? We're going to examine the variability of our predictions using bootstrapping techniques. Our goal is to deduce information about the population from which the original samples were drawn. And to start, let's have a look at this. Here we've got a regression model, and our regression model says that our y coordinates are some slope m, which is a number we don't know, but we believe exists in the population, times x, plus b, this, again, another number that we don't know, the intercept, plus some error. And the error is normally distributed with mean zero and standard deviation sigma, some number we, again, don't know. What we've got here is importing a whole number of different data science packages, and also defining a whole bunch of functions that you've seen in the textbook, the standard units, converting an array of numbers to standard units, a function to compute the correlation coefficient from a table, and the labels of the columns, the slope, the intercept of the regression lines, a function to provide all the predicted values for y given the x values and the y values in the table. A a function to provide the fitted value for a particular x value, function to define the residuals, scatter fit, and also to plot the residual plots. And then here's a nice function called draw and compare that will draw some very nice plots for us. So we'll see in a moment. What draw and compare is going to do is it's going to take a line, in this case with slope 4 and intercept 1, and it will create, in this case, 5 points off this line, which have just been randomly selected in terms of the x values, and then we take our y value equal to the value on our true line, and then we're going to push the points off by a certain randomly generated amount. Okay, so this is the data that has been created. What we get to see is these 5 points, and we'll fit a line of best fit to that. Here's the line of best fit. It's our estimate of the true line, and then here's a picture of both our line of best fit in gold and the true line in green. And you can see we've done pretty well with 5 points. You might say, well, could we do better with 50 points? Here's 50 points that have been generated on the same slope 4, intercept 1 line. And you can see they're clustered around the line. There's small variations. They don't usually lie on the line because of the noise. And we don't get to see the line. We get to see these 50 points. We can plot our regression line. And you can see that our regression line and the actual green line that generated the data are very, very close to each other, and much better fit than when we just had 5 points. If you have 500 points, you get a whole cloud of points around this green line, and we get to see the cloud. We don't get to see the green line, but we can fit a regression line to these points. And again, our regression line and the green line are incredibly close. And finally, if you had 5,000 points, your cloud would look like this, your data would look like this, and you could fit a regression line to that data. And here again, the regression line is an incredibly good fit to the true line. Well, that's very promising. It suggests that with a reasonable number of samples, we should be able to estimate the true line very well with the regression line.